Now we'll start with Gibbs Phase Rule. So this is very important because a lot of question comes in UPSC where you have to take aid from Gibbs Phase Rule to explain your answers. So Gibbs Phase Rule is given by this formula F equals to C minus P plus 2. This is very important formula for you to remember, where F is the degree of freedom. I repeat, F is the degree of freedom, C is the component in the system, P is the different phases of the system. P can also be defined as phi. Okay, it can be written as phi also. Phi is a symbol, right? Phi. So F is the degree of freedom, C is the component minus phases, number of phases in the system plus 2. Okay, this is the formula of Gibbs phase rule. Let's now read it. The Gibbs phase rule relates the number of phases P, components C, and degree of freedom F in a thermodynamic system at equilibrium. Okay, the rule helps determine how many variables are needed to specify the system's equilibrium state. So to have a mineral and being in an equilibrium state, it needs to be under certain equation, right? It needs to follow a certain equation, which is the Gibbs phase rule, so that we can understand how many variables can change in that specific field. As we progress, we will understand it in a better way. So let's give the definition of the different components here. So first is the component itself. C is independent chemical constituents in the system. For example, in a mixture of water and ethanol, there are two components, water and ethanol. Okay, so this is an example of two component. Next is phases. Phases means physically distinct homogeneous part of the system. For example, in a mixture of ice and water at equilibrium, there are two phases, solid ice and liquid phase, liquid water. Okay, but the component will be one because that is H2O. One component will be there, but two phases will be there because it is solid ice and liquid water are present. So two phases, but only one component will be there, that is H2O. Next is degree of freedom F. So independent variable, example pressure and temperature are degree of freedoms that can be varied without changing the number of phases. This degree of freedom indicates how many variables must be specified to completely determine the state of the system. Okay, I know this is little bit will be hazy to you, this degree of freedom, but as we progress, you will understand this in a clear way. So first we'll discuss the one component system where there is only one component. There can be many phases, but it will have only one component, that is C equals to 1. So we'll discuss one component system of water, that is H2O. Okay. So here is the graph on the right hand side of a one component system. This is the pressure, this is the temperature, is increasing towards right, is increasing towards top, and this is the one component system of water. And these are the different phases. Say ice is a different phase, water is a different phase, vapor is a different phase, and supercritical fluid is a different phase. Okay, so these are the different phases. Above this, in supercritical fluid, it is very hard to define a one component system, that is a H2O. So this is actually undefined area. Okay, up to this part, this is totally defined, but here we will see how this undefinition is coming up. So a system in which only one chemical substance is present. Okay, so a system where only one chemical substance is present. Example is water, ice, and steam. So example can be water, ice, and steam. Okay. The phase diagram of a one component system is a PT diagram. This is a PT diagram of pressure and temperature. The PT diagram shows the regions of stability of the different phases of the substance. So it shows the regions of stability of the different phases of the substance. The solid phase ice at minus 5 degrees Celsius to 0 degrees Celsius. So this is a solid phase ice marked by light blue color, having only one phase, that is solid ice at 0 dash to 0. Okay, at 0 dash to 0. this whole area. Here you can see the component is obviously 1 because this is a whole a one component system only. Phase is also 1. See, here is only one phase, that is ice. We are talking about this whole region. Any point you take in this region, we are talking about any point in this region only. Okay. So component is 1, phase is also 1. So what will be the degree of freedom? F equals to 1 minus 1 plus 2, that is 2. So degree of freedom can be 2. So we can vary pressure and temperature throughout this area, right? We can vary pressure and temperature throughout this area. So F equals to 2, degree of freedom is 2. Variables are pressure and temperature can be varied independently without changing phases, as uh, the degree of freedom is 2. So I think you understood now. So in any phase, in any one phase, okay, say ice or water or vapor, any one phase is there, and the component is obviously 1 here in this diagram. So with any one phase, C equals to 1, F equals to 1 minus 1 plus 2, that is degree of freedom 2. So in this phase, we can vary the pressure temperature independently. That means pressure and temperature is not dependent. Okay, not dependent here. Next is, say, this line, solid liquid equilibria. Solid liquid equilibria, that is DB, the DB line. Okay, BD, this line. This line here, you see that we are bounded by two phases, that is ice and water. We are getting two phases, ice and water. But again, the component will remain as it is 1, but the phase is changing, that is phase is now coming to 2. Phase is now 2. In the previous example, the phase was 1. In this example, the phase is 2, right? The phase equals to 2, so degree of freedom will be 1, right? Why 1? Because here it comes 2 minus 1, sorry, 1 minus 2 plus 2 is 1. So here it will be 1. Here degree of freedom will be 1, right? C minus P plus 2 will be 1. C equals to 2, uh, phase equals to 2, and it will be 1, right? So sorry, here C is equals to 1, phase equals to 2, so it will be 1. Variables are P cannot vary independently without changing the place. Here you can see in this line, if we are taking a certain P, the temperature will automatically be assigned to it. Say in this point, if we are fixing a pressure here, then in this point, at this point, we automatically getting a fixed temperature. Say at this point, if we are fixing, say, temperature here now, say we are fixing a temperature at O, then automatically the O dash pressure will be fixed. That means at any point in this line, at any point in this line B and D, if we are fixing one variable, that is temperature, then the another variable will automatically be fixed. That means pressure and temperature, that means the two variables at this line are not or sorry, are dependent on each other. At this line, the pressure and temperature, that means the two variable, are dependent on each other. Okay, so variables P cannot vary independently without changing the phase. P cannot vary independently without changing the phase. If you simply increase the P at B, we will enter the complete liquid phase. To increase P without changing phase, we need to increase pressure along the water ice equilibrium line. There must be exist del P below this line. So this simply explains anywhere if there is a one phase, we will have a degree of freedom 2, and we can change pressure temperature accordingly, and they are not dependent to each other, they are independent. Whereas any line, if you are talking about any line, say BD, BC, AB, here any line, we are getting degree of freedom as 1. So if we are fixing pressure, temperature will automatically get fixed. If we are fixing temperature, pressure will automatically get fixed. That means degree of freedom is 1, and pressure and temperature, that is the two variable, are dependent on each other. Okay, so again, now liquid vapor equilibria, will be vapor liquid equilibria B and C, or say, yeah, B and C. So here again, degree of freedom is 1, Pressure and temperature can varied. Uh, I think there is some mistake here. Pressure temperature will not vary. Okay, will not vary because F equals to 1. Pressure and temperature will not vary. I'll ask the coordinator to change this. Okay. Then there is triple point, that is 0.01 degree Celsius, 611 Pascal. So phase is 3, F equals to 0. So at triple point, remember. So at a single area or the phase, degree of freedom will be 2. At a line, degree of freedom will be 1. And in a single point, degree of freedom will be 0. That means pressure and temperature are already fixed. You cannot manage any of the things. So pressure is fixed, temperature is also fixed. Here say triple point, solid ice, liquid vapor, liquid water and water vapor coexist. F equals to 0. Variable is no variable can be varied independently. No variable can be varied independently. Okay. And at the critical point at 374 degrees Celsius, 22.1 millipascal, here at the critical point, supercritical point, we will have phase equals to 1 because liquid and vapor phases becomes indistinguishable at this point. So it is indistinguishable at this point, cannot be defined. Okay, so liquid and vapor phases cannot be defined at this point, so phase equals to 1. So F will again be 2. Okay, F will again be 2. Variables are pressure and temperature can be varied independently once again. So I'll just give you an overview. So where there is only one phase, we will have F equals to 2. At any line which is bounded by two phases bounded by two phases, will give degree of freedom equals to 1. And at any triple point junction, F equals to 0. That means P and T are fixed. Yeah, fixed. If P is fixed, then T will automatically get fixed. We can only one variable can change, the other will automatically fix, whereas here they are independent. Okay, so this is the explanation of Gibbs rule, and these are the main fundamentals of Gibbs rule.